In mathematics, a vertex operator algebra is an algebraic structure that plays an important role in conformal fields theory and string theory. In addition to physical applications, vertex operator algebras have proven useful in purely mathematical contexts such as monstrous moonshine and the geometric Langlands correspondence. The related notion of vertex algebra was introduced by Jbourjai in 1986, motivated by a construction of an infinite-dimensional Lie algebra due to Frenkel. In the course of this construction, one employs a Fock space that admits an action of vertex operators attached to lattice vectors. Jbourjai formulated the notion of vertex algebra by axiomatizing the relations between the lattice vertex operators, producing an algebraic structure that allows one to construct new Lie algebras by following Frenkel's method. The notion of vertex operator algebra was introduced as a modification of the notion of vertex algebra by Frenkel, Lepofsky, and Mermin in 1988. As part of their project to construct the moonshine module, they observed that many vertex algebras that appear in nature have a useful additional structure, and satisfy a bounded below property with respect to an energy operator. Motivated by this observation, they added the Virasoro action and bounded below property as axioms. We now have post hoc motivation for these notions from physics, together with several interpretations of the axioms that were not initially known. Physically, the vertex operators arising from holomorphic field insertions at points in two-dimensional conformal field theory admit operator product expansions when insertions collide, and these satisfy precisely the relations specified in the definition of vertex operator algebra. Indeed, the axioms of a vertex operator algebra are a formal algebraic interpretation of what physicists call chiral algebras, or algebras of chiral symmetries, where these symmetries describe the ward identities satisfied by a given conformal field theory, including conformal invariance. Other formulations of the vertex algebra axioms include Jbourjai's later work on singular commutative rings, algebras over certain operads on curves introduced by Huang, Kreis, and others, and D-module theoretic objects called chiral algebras introduced by Alexander Beilinson and Vladimir Drinfeld. While related, these chiral algebras are not precisely the same as the objects with the same name that physicists use. Important basic examples of vertex operator algebras include lattice VOAs given by representations of affine KAC-Moody algebras, the Virasoro VOAs in the moonshine module V, which is distinguished by its monster symmetry. More sophisticated examples such as affine W algebras and the chiral DRHAM complex on a complex manifold arise in geometric representation theory and mathematical physics. Formal definition: vertex algebra. A vertex algebra is a collection of data that satisfy certain axioms. Data of vector space V, called the space of states. The underlying field is typically taken to be the complex numbers. Although Jbourjai's original formulation allowed for an arbitrary commutative ring, an identity element 1V, sometimes written or omega to indicate a vacuum state, an endomorphism T, VV, called translation, a linear multiplication map Y, VVV, where V is the space of all formal Laurent series with coefficients in V. This structure is alternatively presented as an infinite collection of bilinear products UNV, or as a left multiplication map Vn Z plus or minus 1, called the state field correspondence. For each UV, the operator-valued formal distribution Y is called a vertex operator or a field, and the coefficient of Z minus n minus 1 is the operator UN. The standard notation for the multiplication is axioms. These data are required to satisfy the following axioms. Identity: for any UV, U equals UZ0 and Y1 U plus ZV, Z. Translation: T equals 0, and for any U, VV. Locality: For any u, v, there exists a positive integer n such that equivalent formulations of locality axiom. The locality axiom has several equivalent formulations in the literature, e.g., Frenkel-Lepofsky-Merman introduced the Jacobi identity, where we define the formal delta series by. Borchards initially used the following identity. For any vectors u, v, and w, and integers m and n we have. He later gave a more expansive version that is equivalent but easier to use. For any vectors u, v, and w, and integers m, n, and q we have. Finally, there is a formal function version of locality. For any u, v, w, v, there is an element such that y,y,w and y,y,w are the corresponding expansions of in v and v. Vertex operator algebra. A vertex operator algebra is a vertex algebra equipped with a conformal element omega, such that the vertex operator y is the weight to Virasoro field L, and satisfies the following properties. Lm lane equals Lm plus n plus CIdV, where C is a constant called the central charge, or rank of V. In particular, the coefficients of this vertex operator endow V with an action of the Virasoro algebra with central charge C. L0 acts semi-simply on V with integer eigenvalues that are bounded below. Under the grading provided by the eigenvalues of L0, the multiplication on V is homogeneous in the sense that if U and V are homogeneous, then U and V is homogeneous of degree dag plus dag minus n minus 1. The identity 1 has degree 0, and the conformal element omega has degree 2. L-1 equals T. A homomorphism of vertex algebras is a map of the underlying vector spaces that respects the additional identity, translation, and multiplication structure. Homomorphisms of vertex operator algebras have weak and strong forms, depending on whether they respect conformal vectors. Commutative vertex algebras. A vertex algebra V is commutative if all vertex operators commute with each other. This is equivalent to the property that all products YV lie in V, Z. Given a commutative vertex algebra, the constant terms of multiplication endow the vector space with a commutative ring structure, and T is a derivation. Conversely, any commutative ring V with derivation T has a canonical vertex algebra structure, where we set YV equals U1 V Z0 equals UV. If the derivation T vanishes, we may set omega equals 0 to obtain a vertex operator algebra concentrated in degree 0. Any finite-dimensional vertex algebra is commutative. In particular, even the smallest examples of non-commutative vertex algebras require significant introduction. Basic properties. The translation operator T in a vertex algebra induces infinitesimal symmetries on the product structure, and satisfies the following properties. Y1 equals EZTU. 2 equals U21, so T is determined by Y. Y equals D, DZ. XI minus XT equals Y equals Y. YV equals EZTYU. For a vertex operator algebra, the other Virasoro operators satisfy similar properties. XL0 YX minus L0 equals Y. EXL1 U minus XL1 equals YL1 minus 2L0 U. Z minus 1. For all M minus 1. For any U, V, WV, the element given in the definition also expands to YV, X, W in V. The associativity property of a vertex algebra follows from the fact that the commutator of Y and Y is annihilated by a finite power of ZX, i.e., one can expand it as a finite linear combination of derivatives of the formal delta function in, with coefficients in end. Reconstruction. Let V be a vertex algebra, and let yar be a set of vectors, with corresponding fields yar and Z plus or minus 1. If V is spanned by monomials in the positive weight coefficients of the fields, Then we may write the operator product of such a monomial as a normally ordered product of divided power derivatives of fields. Specifically, more generally, if one is given a vector space V with an endomorphism T in vector 1, and one assigns to a set of vectors a set of fields and Z plus or minus 1 that are mutually local, whose positive weight coefficients generate V, and that satisfy the identity and translation conditions, then the previous formula describes a vertex algebra structure. Example: the rank 1 free boson. A basic example of a non-commutative vertex algebra is the rank 1 free boson, also called the Heisenberg vertex operator algebra. It is generated by a single vector B, in the sense that by applying the coefficients of the field B equals y to the vector 1, we obtain a spanning set. The underlying vector space is the infinite variable polynomial ring C, x1, x2, where for positive n, the coefficient Bn of y acts as multiplication by xn, and Bn acts as n times the partial derivative in xn. The action of B0 is multiplication by 0, producing the momentum 0 Fock representation V0 of the Heisenberg Lie algebra, i.e., induced by the trivial representation of the subalgebra spanned by Bn, n0. The Fock space V0 can be made into a vertex algebra by following reconstruction, where denotes normal ordering. The vertex operators may also be written as a functional of a multivariable function f as, if we understand that each term in the expansion of f is normal ordered. The rank n free boson is given by taking an n-fold tensor product of the rank 1 free boson. For any vector B in n-dimensional space, one has a field B whose coefficients are elements of the rank n Heisenberg algebra, whose commutation relations have an extra inner product term. Bn Cm equals n delta n m. Example: Virasoro vertex operator algebras. Virasoro vertex operator algebras are important for two reasons. First, the conformal element in a vertex operator algebra canonically induces a homomorphism from a Virasoro vertex operator algebra, so they play a universal role in the theory. Second, they are intimately connected to the theory of unitary representations of the Virasoro algebra, and these play a major role in conformal field theory. In particular, the unitary Virasoro minimal models are simple quotients of these vertex algebras, and their tensor products provide a way to combinatorially construct more complicated vertex operator algebras. The Virasoro vertex operator algebra is defined as an induced representation of the Virasoro algebra. If we choose a central charge C, there is a unique one-dimensional module for the subalgebra C, Z plus K, for which K acts by SID, and C, Z acts trivially, and the corresponding induced module is spanned by polynomials in Ln equals Z minus n1 Z as n ranges over integers greater than 1. The module then has partition function. This space has a vertex operator algebra structure, where the vertex operators are defined by, and the fact that the Virasoro field L is local with respect to itself can be deduced from the formula for its self-commutator, where C is the central charge. Given a vertex algebra homomorphism from a Virasoro vertex algebra of central charge C to any other vertex algebra, the vertex operator attached to the image of omega automatically satisfies the Virasoro relations, i.e., the image of omega is a conformal vector. Conversely, any conformal vector in a vertex algebra induces a distinguished vertex algebra homomorphism from some Virasoro vertex operator algebra. The Virasoro vertex operator algebras are simple. except when C has the form 1 to 62 pq for coprime integers p, q strictly greater than 1. This follows from Kak's determinant formula. In these exceptional cases, one has a unique maximal ideal, and the corresponding quotient is called a minimal model. When P equals Q plus 1, the vertex algebras are unitary representations of iris or ρ, and the modules are known as discrete series representations. They play an important role in conformal field theory in part because they are unusually tractable, and for small p. They correspond to well-known statistical mechanics systems at criticality, e.g., the Ising model, the tricritical Ising model, the three-state Potts model, etc. By work of I-Kang Wang concerning fusion rules, we have a full description of the tensor categories of unitary minimal models. For example, when C equals 1/2, there are three irreducible modules with lowest L0 weight 0, 1/2, and 1/16, and its fusion ring is Z, X, Y. Example: WZW vacuum modules. By replacing the Heisenberg-Lie algebra with an untwisted affine KAC-Moody Lie algebra, one may construct the vacuum representation in much the same way as the free Boson vertex algebra is constructed. Here, WZW refers to the West-Zumino-Witten model, which produces the anomaly that is interpreted as the central extension. Concretely, pulling back the central extension along the inclusion yields a split extension, and the vacuum module is induced from the one-dimensional representation of the latter on which a central basis element acts by some chosen constant, called the level. Since central elements can be identified with invariant inner products from the finite-type Lie algebra, one typically normalizes the level so that the killing form has level twice the Joule-Coxeter number. Equivalently, level 1 gives the inner product for which the longest root has norm 2. This matches the loop algebra convention, where levels are discretized by third cohomology of simply connected compact Lie groups. By choosing a basis yar of the finite-type Lie algebra, one may form a basis of the affine Lie algebra using yan equals yar Tennessee together with a central element k. By reconstruction, we can describe the vertex operators by normal ordered products of derivatives of the fields when the level is non-critical, i.e., the inner product is not minus 1/2 of the killing form. The vacuum representation has a conformal element, given by the Sugawara construction. For any choice a dual basis yar with respect to the level 1 inner product, the conformal element is and yields a vertex operator algebra whose central charge is. At critical level, the conformal structure is destroyed, since the denominator is 0. But one may produce operators lane for n-1 by taking a limit as k approaches criticality. This construction can be altered to work for the rank 1 free boson. In fact, the Virasoro vectors form a one-parameter family omega S equals 1/2 x12 plus sx2, endowing the resulting vertex operator algebras with central charge 1 minus 12 2. When S equals 0, we have the following formula for the graded dimension. The rank n-free boson then has an n-parameter family of Virasoro vectors, and when those parameters are 0, the character is Qn, 24 times the weight minus n, 2 modular 4 mater minus n, modules. Much like ordinary rings, vertex algebras admit a notion of module, or representation. Modules play an important role in conformal field theory, where they are often called sectors. A standard assumption in the physics literature is that the full Hilbert space of a conformal field theory decomposes into a sum of tensor products of left-moving and right-moving sectors. That is, a conformal field theory has a vertex operator algebra of left-moving chiral symmetries, a vertex operator algebra of right-moving chiral symmetries, and the sectors moving in a given direction are modules for the corresponding vertex operator algebra. Given a vertex algebra V with multiplication y, a V-module is a vector space M equipped with an action ym, vmm, satisfying the following conditions. Ym equals idm for any u, vv, wm. There is an element such that ym, ymw and ymv, x, w are the corresponding expansions of in M and M. Equivalently, the following Jacobi identity holds. The modules of a vertex algebra form an abelian category. When working with vertex operator algebras, the previous definition is given the name of weak module, and V-modules are required to satisfy the additional condition that L0 acts semi-simply with finite-dimensional eigenspaces and eigenvalues bounded below in each coset of Z. Work of Huang, Lepovsky, Miyamoto, and Zhang has shown at various levels of generality that modules of a vertex operator algebra admit a fusion tensor product operation, and form a braided tensor category. When the category of E-modules is semi-simple with finitely many irreducible objects, the vertex operator algebra V is called rational. Rational vertex operator algebras satisfying an additional finiteness hypothesis are known to be particularly well behaved, and are called regular. For example, Zhu's 1996 modular and variance theorem asserts that the characters of modules of a regular VOA form a vector-valued representation of SL2. In particular, if a VOA is holomorphic, i.e., its representation category is equivalent to that of vector spaces, then its partition function is SL2 invariant up to a constant. Huang showed that the category of modules of a regular VOA is a modular tensor category, and its fusion rules satisfy the Verlinde formula. To connect with our first example, the irreducible modules of the rank 1 free boson are given by Fock spaces V lambda with some fixed momentum lambda, i.e., induced representations of the Heisenberg Lie algebra, where the element B0 acts by scalar multiplication by lambda. The space can be written as C, x1, x2, V lambda, where V lambda is a distinguished ground state vector. The module category is not semi-simple, since one may induce a representation of the abelian Lie algebra where B0 acts by a non-trivial Jordan block. For the rank n free bosons, one has an irreducible module V lambda for each vector lambda in complex n-dimensional space. Each vector BCn yields the operator B0, and the Fock space V lambda is distinguished by the property that each such B0 acts as scalar multiplication by the inner product. Unlike ordinary rings, vertex algebras admit a notion of twisted module attached to an automorphism. For an automorphism sigma of order n, the action has the form VMM, with the following monodrome I condition. If UV satisfies sigma U equals xpu, then n equals 0 unless n satisfies n plus k, nz. Geometrically, twisted modules can be attached to branched points on an algebraic curve with a ramified Galois cover. In the conformal field theory literature, twisted modules are called twisted sectors, and are intimately connected with string theory on orbifolds.